Hi again, guys. Okay, I know last lesson I said that we would go on to the subject of black body radiation, but actually I just want to do a lesson on how light is emitted, because part of that is to do with quantum mechanics, and we were dealing with quantum mechanics the last lesson, so I thought I'd stick it in together. So we're going to be looking at how lights can be emitted from small particles, atoms or molecules. So there are different ways in which atoms or molecules can emit light or electromagnetic radiation, and we're going to be looking at these ways. And we won't only be looking at how light can be emitted from small particles, but how it can be absorbed also. Okay, can you remember last lesson I said that photons had to come in full numbers? It's not possible to get, for example, 1.7 photons or 1.5 photons or 3.2 photons. They have to be full numbers, 3 photons, 5 photons. So I'm going to explain the reason why that is. First of all, we need to start off with the fact of what an electron is. In chemistry, when you are first taught about electrons, you were probably taught that they're particles. True, but they are also waves. In fact, physicists call them wave particles. So they're particles, but they have wave properties. So in diagram 1 here, I've actually drawn an electron as a wave. Right? So it's 1, 2 waves here. Now if we look at diagram 2, I've drawn an atom, and in the middle of the atom that's the nucleus, right? And around the outside I've drawn the electron ring, a ring where in classical physics you sort of draw the electron whizzing around the ring. Okay? But what I want you to think of these rings as is different energy levels, and we're going to see why the energy levels, they have to be in full numbers. They have to be quantized. You can't get, for example, 2.5 or 2.7 energy levels. It has to be a full number, 3, 4, 5. So think of this ring as an energy level. Now the electron behaves like a wave, and on this particular ring or this particular energy level, let's look at the electron and actually what it's doing as a wave. Let's count how many waves. 1 wave, 2 waves. So there are 2 complete waves here. Let's now have a look at diagram number 3. Right? So I've actually written 4 waves here, and I think we can probably count 4 waves. 1 wave, 2 waves, 3 waves, and 4 waves. So everything working out very well now. Let's go to diagram number 4, and here I've tried to draw 1.5 waves around this ring or this energy level. So let's count the 1.5 waves. So 1, and a half. Okay, so we've actually gone around the energy level or the ring once, yes, and we're back to the beginning again. So let's see what happens if we then continue to make, for example, 2 waves, but at this frequency. So let's count again. Notice we're going over the top of the ring. That's 1. 2. Well, that's quite interesting, because the first time we went around, right, we went over the top, and then we went underneath, and then we went over the top, and now we're going underneath again, but we're directly underneath this blue line here, right? So now you can imagine if this is a wave, let's say this is positive charge up here, and this is negative charge down here. So the positive and the negative are actually going to cancel each other out. So what happens when they're cancelled out? Well, it means that there's nothing there. And if we were to continue around this ring, or this energy level, the wave would disappear because of this positive and negative effect happening at the same time. So this explains why you can't, for example, have half a wave, or you can't have 0.7 of a wave. It has to be either one wave, two waves, three waves, four waves, five waves. You can't have fractions of waves. In diagram 5 I've shown this. Let's pretend this is an atom. Okay, there's the nucleus in the middle. Right, the first energy level is one wave. The second energy level is two waves. The third energy level is three waves. And it's not possible to have electrons whizzing around an energy level halfway between the second ring and the third ring. They've actually got to be directly on this energy level. So now you know that the energy levels have to be full numbers. They can't be half numbers or quarter numbers. Let's explain what happens when we look at an electron, for example, on one of these energy levels. Let's pretend there's an electron whizzing around this energy level here. And then, for example, we give this atom some extra energy, and because the atom has extra energy, the electron gets excited and it will jump to an outer ring. Now the trouble is, when it jumps to an outer ring, the electron feels unstable and it wants to jump back again, and when it jumps back again, it's losing energy, because this is a higher energy level here and this is a lower energy level here, and because it's losing energy, it actually loses the energy in the form of light. Very often it's ultraviolet light, but it can be lights of different colors. Very often the colors you see around you are light emitted through this process. So let me explain that again. There's an electron on energy level number 1. Then if we excite this electron by giving the atom extra energy, the electron could jump to level 2. So now it's on level 2, right? And then, but it feels unstable on level 2, right? And it wants to jump back to level 1 again, right? Level 2 is higher energy, level 1 is lower energy. So when it jumps back, it must mean that the atom loses energy, and it loses this energy in the form of a photon, right? And this photon is light, very often UV energy, but it can be visible light as well. Okay, so I hope that's clear. That's the first method in which atoms can emit electromagnetic waves or light.